Assalamualaikum and good day everyone. We are from Group 2 Section 4. Today we will present about our project which is the title is a high speed sensor captures the following current during a control circuit interruption. Before we start, I would like to introduce our group members. First we have Azam Hakim bin Abdullah, number matrix DE 250106. Next, we have Amirul Abid bin Anamur Rahman, number matrix CE 250054. Next, Muhammad Akmal bin Muhammad Nizam, number matrix AE 230019. And last but not least, myself, Muhammad Hazim bin Salim, number matrix DA 240067. For the introduction, numerical methods are vital for evaluating substation protection reliability. This project analyzed a control circuit interruption where a high-speed sensor captures the current IT readings in amperes. Our goal is to determine the transient decay rate di over dt at t equals to zero point 0.5 seconds. We implement and compare two core numerical approaches to ensure mathematical accuracy. We use the three-point central difference method for fast, real-time derivative estimation and Newton's divided difference method to construct a polynomial that models the continuous current curve. So, our manual calculation are cross-verified using a MATLAB software simulation. Successfully matching our results with the simulation validates the protective relays, internal tripping logic, bridging the gap between theory and practical engineering.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Abid bin Anamur Rahman. My matric number is CA250054. For the methodology section, we have chosen the 3-point central difference method. This method is used to manually calculate the rate of current change in a system based on the formula shown on the screen. We set our target time t at 0.500 seconds with a step size h of 0.125 seconds by plugging in the current values for the forward time and the backward time and then dividing it by 2h. The final result of this manual calculation gives us a value of negative 0.9176 ampere per second. To ensure that our previous manual calculation is valid, we also developed a simulation using the MATLAB software. On the left side of the screen, the source code has been defined to process the exact same input data. Meanwhile, the graph on the right displays the current curve with red dots as the sensor point. The green dash line represents the tangent line at the fault point. If we look at the common window at the bottom, the generated output is negative 0.9176 ampere per second. The proof that our simulation results are consistent and accurate, matching our manual calculation perfectly.
Hi there, my name is Azam Hakim Abdullah with the number matrix BE250106, and I will be presenting the methodology for Newton's divided difference for the manual calculation. So to start off, we have to address the formula. We are using the formula for Newton divided difference, the FIO equals to FI and whatnot and etc. So first of all, we would have to make the table. So we have 1, 2, 3, 4, 5 columns, which is I and then TI and then I and then I and so on and so forth. So the first one is with the I equals to 0. and ti at 0.375. This is the blue ones are given in the question. So at I0, the Ti is equal to 0.375, and then the current value is 1.0260, and then the I at 1, the Ti is equals to 0.5, while the current is equals to 0.925. And then at 2, the time is 0.625, while the current is equals to 0.7966. Moving on to the equation, we basically just have to insert the values into the formula, and we would get on the current at 0. The first one is negative 0.8080, while the 1 at I1 is equals to negative 1.0272. Moving on to the last one, which is at the current on second one, which is equals to negative 0.8768. So now to form the polynomial, we basically just have to insert into the formula again, which is at 1.0260 minus with 0.8080, and we would have to time it with time negative 0.375, and then minus with 0.8768 times with time minus 0.375 times with t minus 0.5. And then we would have to do all the calculations. So before we do that, we would have to find we would have to differentiate the polynomial to basically find the slope, because we need to find the slope, and the slope is the dy dx of the answer. So what we did was we would have to differentiate it first. Hence, we got the final answer to be at negative 0.0408 minus with 1.7536 t. And then we just have to solve for t at 0.5 seconds, which is given in the question. Hence, we will get the final answer to be negative 0.9176 ampere per second. Now moving on to the MATLAB simulation for the Newton's divided difference. To start, we would have to what data we have, which is the time data at 0.375, at 0.5, and at 0.625. And then we also have to tell the current data, which is at 1.0260, 0.9250, and finally at 0.7966. Now the target, which is the t, the time that we needed the question once, is at 0.5. Moving on to the Newton polynomial and derivative calculations. At BO, it is equals to the current data. And then at B1 is equal to at current data 2 minus with current data 1. So this is basically the formula, but in MATLAB code form. And then basically the didt is just a differentiation of the values that we got just now. Moving on to plotting to get the Newton divide difference graph. So basically we just have to do the time, and then we have to put all the values that we need equals to the line space as 0.35, as 0.65, and 100. And then at P2, fine is equals to B0 plus B1, and so on and so forth. And then tangent and everything. And then, yeah, the whole coding from top to bottom is basically just to put it in a graphical form. So at the final answer to be f print equals to method 2 Newton's interpret. This is basically just to tell it so that it's a lot more better to read. And then at final answer at the command window, method 2 at Newton interpolynomial is equals to the same as the manual calculations, which is equals to negative 0.9176 ampere per second.
So for part result and discussion, uh, as you can see from the table, we choose target point at 0.500 second for first method, and second method is also the same. So at manual calculation, we got the output is minus 0.9176 ampere per second, and also for MATLAB simulation output is also the same with the manual calculation for both method. So consistent outcome from this both numerical technique is successfully yield an identical derivative value of negative 0.9176 ampere per second at target point, which is 0.500 second. So for theoretical alignment for first method, which is 3 point central difference, is derived from quadratic interpolant matching the second order Newton polynomial. So basically we derive from first method, and second method is at the same target point. So physical significant in this result, so we get negative value right for both method. So it indicate that uh, is a rapid transient decay, meaning that the fall current drop sharply. If we refer to the MATLAB graph, it also show the graph it drop sharply. So next, from software verification, we do the manual calculation and compare with MATLAB. So it the same, which is it proves that MATLAB and manual calculation is aligned. So for engineering trade-off, central difference is ideal for real-time relay execution, while Newton method is excellent for continuous curve movement.
To conclude, our project successfully met its main objective. We determined that the rate of current change at the critical fault moment is exactly negative 0.9176 amp per second. By integrating two different mathematical approaches, which is the 3 point central difference formula and Newton's divided difference method, we proved that both techniques yield identical reliable results. Our manual work was completely validated by the MATLAB simulation, giving us high confidence in the accuracy of the data. Ultimately, this multi-method framework is crucial for real-world engineering as it ensures that the internal tripping logic of digital protective relays functions correctly to prevent catastrophic failures in electrical substations.